has 1, 2, 3, 4, 5, 6, 7, 8, 9 protons, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 neutrons, and 1, 2, 3, 4, 5, 6, 7, 8, 9 electrons. Now, let's see how many isotopes it has. Just grab this eraser, color it in, erase all this, bring this over here. 18 isotopes, which are all unstable except for fluorine 19. Alright, now let's watch me move fluorine 19 over here into the corner, draw a pretty arrow, and now let's talk about fluorine's percent abundance. Now, since fluorine is the only isotope that basically exists because everything else just decays right away, it has a 100% abundance. So, if we bring the 100% abundance over here into the corner, that means by multiplying the mass of the isotope by the percentage of the abundance, we get fluorine has an 18.998403 average atomic mass, according to my calculations. Just kidding, according to Wikipedia, which also says that fluorine forms a cation. What kind of cation does it form, you may ask? Okay, well, if you take long cat is long, you shrink him down, and you rotate him 90 degrees. There, you get fluorine minus 1, or fluorine to the negative 1. Erase all this. Fluorine to the negative 1 is cation. Well now, ceiling cat, if you'll remember from our periodic table of elements, fluorine is in period 2 of the halogen family, and it has 7 valence electrons, signified by that little hectagon right there. Alright, 1, 2, 3, 4, 5, yeah, hectagon. Now, with those 7 valence electrons, there are 2 ways you can write their electron configuration. The longhand way to write it is 1s2, 2s2, 3p5. And the shortcut way is helium, in brackets of course, 2s2 and 3p5. Going back to our periodic table of elements with a hexagon, not a hectagon, silly David from 48 seconds ago, no element on this entire periodic table has a higher reactivity than fluorine, and we'll look at that later so it can make my video seem longer. Right now, let's take a look at some Lewis dot diagrams. Let's draw the Lewis dot diagram of fluorine. We'll just start off by drawing the nucleus, and then we'll add in the valence electrons. Fluorine has 7 valence electrons, which means that it really wants to have 8, even though it already has 7 perfectly good electrons, or balls of yarn in this case. It's going to come over here, and it's going to find another atom, maybe say chlorine, which also has 7 valence electrons, and it'll form what's known as a covalent bond, where 1 or more electrons are actually shared between the 2. This covalent bond right here will end up being called ClF3, or chlorine trifluoride. Similarly, we can start over and we can form an ionic bond, which is a metal and a non-metal, and to demonstrate what this looks like, we'll take sodium and fluoride and we'll bond them together, and what sodium will actually do is it'll give away its electron because it's a metal and a non-metal in an ionic bond. And we all know that, of course, metals are all dogs. That's it. Alright, let's just sit back and watch the fluorine chemical reactions.
Going into the apparatus, it's going into this tube. Martin, you can't see anything, can you? You can't see anything at all. And that's because there's only a little under 2 atmospheres of fluorine in there. Okay, so I'm now going to cool this down with liquid nitrogen to minus 196. I'm going to do it slowly. It will take a little while. Okay, Martin, do you want to help me with this? So what I want to do is for you to take that jar away, and then I'll slide this one in. So just slide it away and back up again. And there we have, nearly 2 inches maybe of liquid fluorine. And here is just a scouring pad. Basically, it's a metal scouring pad, iron wool.
It's burnt a hole right through the iron wool. It's extraordinary. The iron looks as if it's rusted, but the rusty colour is actually iron fluoride, or maybe a bit of iron oxide from the hot iron reacting with the oxygen in the air. Well, the reason that fluorine makes such strong bonds is because it is a small atom and the nucleus is relatively highly charged because it's right on the right-hand side of the periodic table, but the electrons don't shield this nucleus, so it is very so-called electronegative. It attracts electrons to itself from other elements. So we haven't done anything. This is cold charcoal and cold gas, and the gas just touching it is enough to start the fire. Think of that, just the cold gas setting things on fire. Most chemists are really too frightened to work with fluorine. You can't use it in glass vessels. It doesn't attack glass, but if the glass is a tiny bit wet, and most glass has moisture absorbed to it, then the fluorine forms hydrogen fluoride when it reacts with the water, and the hydrogen fluoride just eats through the glass. So you need to use equipment made out of metal, usually nickel, and the fluorine reacts with the surface of the nickel the first time you use it, and then you get a layer on the surface that protects the rest of the metal.
So this is again fluorine with sulfur, so you're going to oxidize the sulfur probably to sulfur tetrafluoride or sulfur hexafluoride.
Fluorine has this reputation for being very reactive and very dangerous and something to be careful about. But aren't there fluorine atoms in my toothpaste?
There are. Your toothpaste contains fluoride. And just in the same way that you can eat sodium chloride table salt, which contains chlorine, you can use fluorides, and once the fluorine has got an extra electron, for example, from the tin in tin fluoride, which is often used in toothpaste, or sodium fluoride, it's got what it wants, and it's not very reactive. And the way it works with teeth is that the enamel of your teeth is a compound of calcium called apatite, which normally the apatite in your teeth can dissolve quite easily in acid. For example, if you eat sweets or drink some fizzy drinks, they have enough acid to start dissolving the surface of your teeth. But if you brush your teeth with fluoride, some of the apatite, which contains OH groups, some of these are replaced with fluoride, and you make a material called fluoroapatite, which is much less soluble in acid, so it can't be attacked so easily, so you don't get holes in your teeth.
Oh,